let me start by telling you a little bit about, the underlying fluid dynamics. These are called Lagrangian fluid dynamics. And here's a little overview of my talk. I will talk about the fluid dynamics, which are called Lagrangian fluid dynamics. Then I will tell you about an example that we studied, which was a Chinese restaurant in Guangzhou. This was one of the first cases that where people realized that the virus was probably being carried by the airflow. And then I'll talk about, the consequences of the simulation and the observations one can make. And at the end, I will end up on a note how one might be able to mitigate, the spread of the virus through the air. So the first question is how this works. The airflow, when somebody exhales the virus, the airflow is turbulent and random. The virus particles or the aerosols are going to go in different directions. But it turns out that if we take an average over many exhale events, then we can actually compute the statistical average of the flow. And what we get is a cloud of particles propagating in a direction, usually driven by air conditioning or the ambient airflow. And this cloud consists of small droplets and aerosols, which are passive scalars. And what that means is that they don't influence the flow, but they are carried by the flow. And we have a nice theory of passive scalars in Lagrangian airflow that we can utilize. Now, in Lagrangian flow, the observer follows the droplets or the aerosols, and that's precisely the point of view we want to take. And it's distinct from Eulerian flow, where the observer is basically stationary and the flow goes by. So what enables us to do this is we are able to compute the statistical average of the structure functions, and it turns out that they determine the cloud and how it propagates. So let's look at the layout of the I'm going to try to, share a different program where I can actually do the, look at this on a full screen mode. Let me see if that works. Okay, I think this is a little better. Can you see my screen?
No, doctor, actually.
Pardon?
No, we can't see your screen.
You can't see my screen. Okay, let me see if I can. Very good. Maybe I have to share first and then.
Yes, yes, doctor.
I can spread this. Let me do that. Okay. Okay. This is very good. Yes, there we go. Okay, now you should be able to see it.
Yes, yes, please.
And now I'll do the full screen mode. Yeah, I apologize for this, but
Yes,
all
I
right.
understand.
So we're going to look at this Lagrangian airflow, and we went through this slide already. So let me now turn to the Chinese restaurant. And this was a contagion that took place in early January in Guangzhou in China. And we had 3 families who were sitting at separate tables. One of the families had traveled from Wuhan, where the pandemic started, and ate lunch in the restaurant where the other families were present. And one traveling family contained 1 person who fell ill later that same day and went to the hospital. But 12 days later, 9 members of the 3 families had fallen ill with COVID-19. However, no one else at the restaurant nor the servants fell ill, and only the people in the direct airstream of an air conditioner that was probably blowing warm air at the time fell ill. And here is a picture of the restaurant. What you can see is that there are 3 tables at the rear of the restaurant. I labeled them A, B, and C. And then there's a bunch of other tables, but there is an air conditioning unit. You know, the second picture is a blow up of this.
Sorry to interrupt you, doctor. We can't, we are unable to see your screen.
You're not able to see my screen?
Yes, yes. You're not able to see.
The sharing is paused. Bro, bring your shared window to the front. How do I do that? Okay. Let me just stop sharing and start it again. Okay. Can you see it now?
Yes, we can see.
Very good.
Thank you.
So here is the diagram again. You know, the top picture shows the whole restaurant, and the tables that I'm talking about are the tables at the rear of the restaurant. And the bottom picture shows those 3 tables. And what you notice is that there is an air conditioning unit on the wall, which is blowing air. But it turns out that the vents that would let in fresh air or let out the contaminated air, they were all closed. So the air was simply recirculating in this closed space. In fact, it was blown by the air conditioning unit along the ceiling because it was warm air. Then it sank along the opposite wall and then came back to the air conditioning ceiling along the tables. Now, we were lucky that people were able to go into this restaurant and do a careful experiment, with a contaminant that they dispersed. I should also say that, the yellow circle here, I hope you can see that, is the infectious person. And the red circles are the people who got infected. And as you can see on the layout, the extent of the restaurant or the width of the restaurant was about 6 meters there. Many of the people that got infected were further away than 2 meters. So the contagion had to be not close contact with the infected person. Now, people actually went into this restaurant and they did an experiment, and then they also did a computational fluid dynamics simulation. And what they saw is that when they blew a blue or contaminant into the air from the place where the infected person was sitting, the contamination was sucked into the into the air conditioning unit and then spread to the restaurant. But notice it was not spread to the whole airspace. It was basically spread into a pyramid, which has its base at the opposite wall, and very little contamination, got into the air above, and also it seems even below the air conditioning unit. However, the people who got infected, and in fact most people, had their head in this contaminated pyramid. So what we do is that we compute the Richardson distribution of the droplets and the aerosols separation. And this is something we can do once we have computed the structure functions in the Lagrangian turbulence. This is what it looks like. It's going to enable us to get the shape of the cloud. And this is what the contaminated area looked like on average. It was a pyramid. The infectious person sat in the middle of the cylinder and blew exhaled virions that were then carried by the airflow. They filled this cylinder, which is shown, and then they were sucked into the air conditioning unit and spread to the whole contaminated pyramid. And this geometry allows us to figure out what was going on. It's interesting to notice that most of the studies and most of the predictions that people use, they assume that the air is well mixed. And what this example shows is that this is not always the case. It really depends on the airflow and the geometry of the space. So this is what the cloud actually looks like. It's a cross-section of the cloud. And what you have to do to get the exact shape is to spin this around the axis, around the x-axis. And then you get the shape of the cloud. It sort of bulges out a little bit closer to the infected person, and then it levels off. And then you can use this to compute what the concentration of droplets and aerosols is. And what you see as a function of time, the families, they stayed in the restaurant roughly an hour. What you see is that in 12 minutes, it's up to 1, and 1 is the normalized unit, which is the concentration next to the person who is infected. So basically in 12 minutes, you get the same concentration in the whole contaminated pyramid as you get if you were sitting right next to the person who is infected. And in 1 hour, you have 5 times that concentration. So you start with a concentration which is not very infectious, but at the end of 1 hour, you end up with a concentration which is very infectious. Now, let me discuss this a little bit. There were a couple of papers that came out earlier that we, based our study on. And the first one speculated that the air conditioning was blowing large droplets from table to table. You can show that that's not the case because the airflow was simply not strong enough to, initiate or carry a ballistic motion by large droplets. And instead, the reason for the contagion was the buildup of these droplets, aerosols, small droplets and aerosols over time. Now, the concentration, as I mentioned, in less than 12 minutes is what it would have been if they were sitting next to the infected person. In 1 hour, it was 5 times that. So in one of the publications which did the EFD simulations. The blame for the outbreak was the poor air conditioning in the restaurant. That's true because no fresh air was coming in and there was no filter, to filter out the droplets and the aerosols. But we tried to put in what's recommended, air conditioning. So we put in 8 liters a second per person. And it turned out that that didn't make much of a difference. The concentration still increased what it would be next to the infected person in 13 minutes. And in 1 hour, it was almost 4 times that. So standard air conditioning did not solve the problem. Now, you can compute what the concentration is by solving this differential equation. C here is the concentration, and E is the exhalation rate, and VI is the volume of the pyramid or the volume of the infectious air. Now, lambda is a dissipation coefficient, and it's really a sum of 3 coefficients. One is the dissipation due to ventilation. That was 0 because there was no ventilation in the room. The second one is the settling time of the droplets and the aerosols. And the third one is the decay time of the viruses in the aerosols. And KV was equal to 0. And what most people are doing in their models is taking the settling time not to be equal to 0. And that we believe is a mistake because the settling time is really the settling time of small droplets, which is from 8 to 15 minutes. But it turns out that the evaporation time of these droplets, when they evaporate into aerosols, is only 30 seconds. So basically, everything, the small droplets evaporate immediately into aerosols, and the settling time of the aerosols is practically infinite. They can stay in the air for a long time, especially if they're blown around by the air conditioning. So the only dissipation mechanism is the decay time of the viruses, is the decay of the viruses. And that takes a long time. So instead of the solution of this being an exponential function that puts you in a steady state, and most people assume, you actually get polynomial growth. And I can show you of the, we can simply concentrate on the concentration of the aerosols and forget about the small droplets. They all evaporate. And here is what it looks like, what the concentration looks like as a function of time. The red line on top is the linear growth. There's an orange line, which is this quadratic polynomial that you can hardly see because it coincides with the solution of the OD. So basically, the concentration is following this quadratic polynomial. And here I show it for a little bit longer on the right-hand side. I show it for a little bit longer for 2 hours, and then you can see the orange and the blue line separating a little bit. So the only dissipation, the only thing which is helping the, to decrease the concentration is the decay time of the virions. And that turns out to be, if we assume that the air conditioning is drying the air, so we have a fairly dry air in the restaurant, so we assume 21% relative humidity, then that turns out to be 0.0031. It is very small. So you follow, so what happens is that over an hour, the concentration is increasing a lot. And you can end up with a concentration at the end of the hour, which is quite dangerous. So let me now explain just briefly what the concentration of virions are represented by the concentration being equal to 1. That's what we normalized it to be. next to the infectious person. And the relevant units here are 50% tissue cultured infectious dose. It turns out that an inhale event will involve 10 to the 4th TCIDs, 50. So this is what we mean by the concentration being 1 next to the infected person. It's actually the concentration of 1.895 times 10 to the 4th TCID 50. Now, unfortunately, it's not known what the infectious dose is, but if we quite arbitrarily say that only 1 in 10 doses are effective, then we roughly get 2,000 TCIDs with 50% infectious dose. We can think about this as 1,000 effective virions. And what this is saying is that in 1 minute, a person sitting next to the infected person will have inhaled 1,000 virions 12 times. And consequently, people sitting next to the infected persons for a sufficiently long time, 10 to 15 minutes, are invariably infected. The suspicion is that this is actually how the virus is mostly getting spread. It's being spread through the air by people being in too close proximity without proper masks. So let me end here with some diagnostics. The first thing to notice is that the well-mixed hypothesis does not apply because the airflow drives the aerosols into a portion, the pyramid of the airspace of the restaurant. So geometry and airflow is very important when one is trying to design safe spaces. The settling time of the small droplets is not relevant because the small droplets evaporate into aerosols long before they can settle. The settling time of aerosols being blown around by the airflow is practically infinite. If there is no fresh air, then the ventilation rate or the dissipation due to ventilation is 0. And thus the concentration grows as a quadratic polynomial. It does not go to a steady state. It continues to grow through the periods which are relevant and stays far below the steady state because K of D, which is 1 over the lifetime of the virions, is very small. So after 1 hour, you can end up with space, even if you only have 1 person, which become quite contagious. And this increases tremendously if a person is doing physical exercise, and exhaling a lot more into the space. However, the necessary flow of fresh air and filtering, which is KV, for safe concentration is now easily computed using the quadratic polynomial. So one can use this machinery to design safe spaces. And that is the end of my talk.